Lastly, we'll talk about calculating the overall K for a reaction that contains a mixture of weak acids and bases. For this example, we're going to revisit the NH4F solution that we considered in our last video. And there is one more possible reaction that could occur. So we looked at the reaction between NH4 plus and water. We looked at the reaction between F minus and water. But you could also do a reaction between the NH4 plus and the F minus ion, right? Because the NH4 plus is an acid and the F minus is a base. So there's no reason why you couldn't react these two with one another. Let's go ahead and write out what this reaction is. And because both are weak, this is an equilibrium reaction. So NH4 plus F minus, again, both are weak, so it's equilibrium. NH4 plus is an acid, so it loses a proton to become NH3. F minus is a base, so it gains a proton to become HF. In this reaction, right, we're neither producing H plus or hydroxide, so you couldn't really use a Ka or a Kb to tell you exactly what this reaction is. This reaction isn't a Ka, it isn't a Kb reaction. This reaction is just a general K. And we want to find what the value of K is for this reaction, given the Ka values for our NH4 plus ion and for the HF molecule. So let's think about how we can use these Ka values to help us find the overall K for the reaction. What I'll do is start by writing what our overall goal of the problem is. So just rewrite the reaction. And we're given the Ka values for the NH4 plus and for the HF. It's not enough to just say, oh, these are the Ka values. We have to also write the reactions that these correspond to. So let's not just write the Ka values, but also write the reactions that they go along with. So for NH4 plus, that Ka value, right, that acid dissociation constant corresponds to the reaction for the dissociation of NH4 plus into H plus NH3. That's what this Ka expression, or that Ka value, goes along with. And we're also given the Ka of HF, 7.2 times 10 to the minus 4. And again, let's think about what that means, right? So that value of 7.2 times 10 to the minus 4 is the acid dissociation constant for HF. This corresponds to the reaction where HF breaks up into H plus and F minus. So these are the Kas that we've been given, and these are the reactions that those correspond to. Now what we need to do is rearrange these reactions so that they will add up to make the goal reaction. We've seen examples on how to do that back in chapter 6 when we talked about doing manipulations of equilibrium reactions and equilibrium constants. So we can start by looking at the goal reaction and taking one substance at a time. First substance that we see here is NH4 plus, and we see that the NH4 plus only appears in this first equilibrium reaction. We want to have one NH4 plus on the left, and we already have that. So we're going to keep the NH4 plus reaction the same. So we're going to say keep the same because you want NH4 plus on the left. Now we'll come back up to our reaction. What we next see is that F minus appears on the left-hand side of the equation. From the information that we were given with this Ka value, in this reaction, F minus appears on the right-hand side of the equation. We want it to be on the left in the goal reaction. And so that means that we need to reverse this HF dissociation reaction. So for this one, with the HF, we need to reverse to put F minus on the left. Or you could also look at it as saying that we want to have HF on the right-hand side. And if you reverse this, you put it on the right-hand side. So now what we're going to do is write these rearranged reactions and add them up to get the goal and think about how we manipulate the K values along the way. So now what we have, the first reaction is unchanged, Still NH4 plus goes to H plus NH3. The K here is still 5.6 times 10 to the minus 10. Because we've reversed the reaction with HF, it now takes the form H plus F minus is at equilibrium with HF. And when you reverse a reaction, I'll remind you that you have to invert the K value. So this is 1 over 7.2 times 10 to the minus 4. Now we can add up these two reactions to get the overall, and in the process, the H plus in this reaction cancels the H plus in that reaction, leaving us with the exact reaction that we're looking for here. NH4 plus F minus is at equilibrium with NH3 plus HF. Right, so all that we did was just to rearrange these Ka reactions to give us the reaction that was indicated in the goal of the problem. And to find the overall K value, I'll remind you that upon adding reactions, you multiply the Ks. So let's multiply these Ks. 5.6 times 10 to the minus 10 times 1 over 7.2 times 10 to the minus 4. When you plug that into your calculator, what you find is that the overall K for this reaction comes out to 7.8 times 10 to the minus 7. There it is. So that's how we're able to find the K, the overall K, for any sort of an acid-base reaction. It helps to write the actual reactions that the given Kas correspond to, and then think about how they can be manipulated and rearranged to get you the reaction that the problem is asking for. Now, having found that the value of K for this reaction is 7.8 times 10 to the minus 7, it's helpful to think about the significance of this value. This is a very small value of K, indicating that this reaction very heavily favors reactants. It very heavily favors the left-hand side of the equation. And there is a general sort of a idea that comes into play here and becomes very important for a lot of acid-base chemistry. If you have to take organic chemistry, a lot of that is acid-base chemistry, and what I'm about to say next is one of the most important things to know when you're doing organic chemistry. And it's this. When you do an acid-base reaction, equilibrium always favors the side of the reaction that contains the weaker acid, because the weaker acid wants to hold on to its H plus more. This reaction, really any acid-base reaction, is essentially a competition for protons. There's a competition for protons going on between the fluoride ion and the NH3, and it's going to be the weaker conjugate acid that's more likely to hold on to its protons. And so NH4 plus is much more likely to hold on to its protons. It's going to be much more likely to stay in the form of NH4 plus. So equilibrium will always favor the one with the weaker acid. And we could put that in here, right? We know that NH4 plus is a weaker acid because the Ka on the NH4 plus is 5.6 times 10 to the minus 10. And for the HF, the Ka is 7.2 times 10 to the minus 4. So the HF is much more likely to give up its proton and become F minus. The NH4 plus is less likely to do that. The NH4 plus likes to stay as NH4 plus, and so that's why the equilibrium position very heavily favors reactants here. So it's just kind of a nice sort of a general concept to be aware of, and you see that a lot more if you have to take more chemistry classes. With that, we've reached the end of Chapter 7. And so this is our list of concepts that we discussed in this chapter. This is just one of 2 slides that has everything. We did a lot in this chapter. So you could take a look at this list and use it as a study guide if you'd like to. And we're done with Chapter 7.